In this lecture, we are going to study the Frobenius theorem. Given a k-plane distribution on M, or in other words, a vector subbundle of the tangent bundle of dimension k, we want to know whether or not this distribution is integrable. Very roughly speaking, this means that the distribution can be realized geometrically. And the Frobenius theorem provides a characterization of the integrable distributions. Let us introduce the setting of the Frobenius theorem. So let F be a k-plane distribution of M. By definition, this is just a C-infinity vector subbundle of the tangent bundle of M of dimension k, right? And of course, locally, if we have a point x, we can give the distribution by providing k vector fields. Indeed, if we have a point x, there exists always an open neighborhood U of x in our manifold M, and k vector fields in U such that, let's say, the fiber of our vector subbundle f at y is just the subspace generated by the tangent vectors defined by these k vector fields at y. Okay? Of course, in order for this to be true, we need these tangent vectors to be linearly independent for every y. Okay, but this is possible locally. We say that the k-plane distribution f is integrable if for any x we have an immersion of a manifold of dimension k in M such that first the point x is in the image of this immersion, and then the tangent space of essentially the tangent space of n at every of its points is given by the distribution. Okay, in this situation we say that it is integrable, and the image by the immersion of n is called an integral manifold of the distribution through the point x. Okay. Something that it is interesting is that not every distribution is integrable. So let us consider an example. M is going to be R3, and we consider the distribution that is generated by the vector fields x and y. These two vector fields at every point are independent. Okay. Moreover, we have that if we consider the projection pi from R3 to, let's say, R2, that sends xyz to xy, something that happens is that if we restrict this projection to any fiber of our vector subbundle, then the map is indeed a linear isomorphism. Okay? So in particular, if we have an integral manifold, it has to be a graph. Okay? If any integral manifold, it's going to be of the form, it's just a graph, it's of the form C equal to alpha of xy. Okay? But we can actually, we call this S, we can calculate the tangent space of S at any of its points. Okay? The tangent space at a point x0, y0, c0 of S. Okay, we have to realize that is parameterized by xy, alpha xy. I mean, it's the image of this map. So if we want to calculate the tangent space, it's going to be generated by the partial derivative with respect to x. So the vector 1, 0, partial derivative of alpha with respect to x at the point x0, y0. And if we consider the partial derivative with respect to y, we get 0, 1, and this derivative of alpha with respect to y, right? So 0, 1, and this thing, of course, in the point x0, y0, right? But this tangent space has to be generated, this space generated by these two vectors at the point x0, y0. And this is possible if and only if this tangent vector is equal to this one, and this tangent vector is equal to this one. Okay? So in this way, so we have this is the vector field x, then we have y, and what happens is that if we get our graph, we need that the derivative of alpha with respect to x has to be equal to y. Yeah, we saw that in the previous slide. The vector 1, 0 derivative of alpha with respect to x has to be this one. And in order for this submanifold to be an integral manifold, we also need that the derivative of alpha with respect to y is equal to h. But obviously, since we have that this equality of second derivatives, we deduce that the derivative of g with respect to y has to be equal to the derivative of h with respect to x. And if the distribution is integrable, this is a necessary property. So not every distribution is integrable, okay? So the distribution is integrable implies this property over here, okay? But something that you can check out is, it's very simple, is that if this property holds, then the Lie bracket of these two vector fields is 0. So we're gonna get that the Lie bracket of x and y is 0. And then we can use the rectification theorem that says that locally these vector fields can be interpreted as coordinate vector fields. And it is very, very simple to see that the distribution given by coordinate vector fields is always integrable. So what happens is that in this case, we can characterize whether or not the distribution is integrable. And indeed, it is equivalent to this condition on the Lie bracket. So it's in order to know if a distribution is integrable, it's reasonable to expect that we could have a necessary and sufficient condition that depends only on Lie brackets. And indeed, that's what the theorem, that the Frobenius theorem, is going to provide. Motivated by the previous example, we are going to introduce the concept of involutive distribution. Let F be a k-plane distribution on M, so a vector subbundle of the tangent bundle of M of dimension k. We say that F is a Frobenius distribution or also an involutive distribution if for any open subset U of M and any pair of sections X and Y of the restriction of F to U, we have the delete bracket is a section of the restriction of F to U. Okay, but we do not want to check this condition for any open subset of M and any pair of sections. And we are going to give an equivalence condition you can check out that is equivalent to the definition. It suffices to consider an open cover of M such that the restriction of our vector subbundle to any set of the open cover is indeed a trivial vector bundle. So it's generated by k vector fields that never vanish. And then F is involutive if the leaf brackets of these vector fields are sections of the restriction of F to UA for every open set in our cover and every pair of indexes. Okay? This is interesting because in particular it implies that every distribution of dimension 1 is involutive. For dimension 1, here we have just one vector field for every set of the open cover, and the leaf bracket of this vector field with itself is 0. So obviously it's a section of the distribution. Okay, every distribution of dimension 1 is involutive. In a few seconds, we are going to introduce the Frobenius theorem that says that involutive distributions and integrable distributions coincide. So in particular, every distribution of dimension 1 is integrable. But that's something that we already know, because it is essentially the theorem of existence and uniqueness of solutions of ordinary differential equations. Now we can introduce the Frobenius theorem. Consider a k-plane distribution on M. The goal of the Frobenius theorem is characterizing integrable distributions. So the theorem says that the property of being integrable is equivalent to being involutive. And moreover, it's also equivalent to be locally a distribution given in some coordinates by the k-first coordinate vector fields. So locally, it is always a very, very simple distribution. Okay, we want to prove this theorem. Okay, if we consider the distribution, okay, generated by the k-first vector fields in some open subset of Rn, the connected integral manifolds, the integral manifolds, this submanifold over here is always an integral manifold. And if we want to consider connected integral manifolds, then those ones are going to be the connected components of the intersections of sets of this form with B, where of course the CJs are real numbers. And these sets over here are called plaques, okay? Before doing the proof of the Frobenius theorem, let us try to understand a little bit more and very briefly its meaning. So if we have an involutive distribution, it's going to be integrable, and so it's going to define a foliation. A foliation is a partition of M in immersed submanifolds of dimension k, right? And the sets of the partition are called leaves, right? How do we know if two points are in the same leaf? By definition, 2 points x and y are in the same leaf if there exists a sequence of points xj, so that the first one is x, the last one is y, and when we consider 2 consecutive points, then they belong to the same plaque, okay? They belong to some plaque, okay? That's the definition. Okay, so before getting into the proof of Frobenius theorem, let us consider an example. We consider the vector field partial with respect to x plus c times partial with respect to y, where c is an irrational real number. Okay, and now we are going to consider the torus of dimension 2, which is the quotient of R2 by the equivalence relation that identifies xy with x plus 1y and xy with xy plus 1. Indeed, we have a natural projection from R2 to the torus. Okay, and what happens indeed is that this vector field over here is related to a vector field on the torus, okay, whose trajectories are the projections of the lines whose inclination is equal to c. So irrational lines, the projection of by pi of the irrational lines of inclination c, of course. So if we consider now here a trajectory, something like this point is identified with this one, so we have to follow this line. This point is identified with this one, so it's something like this. This point is identified with this one, so something like this. This point is identified with this one. Okay, and now we get something like this and something like this. Okay, and so on and so on. What happens, of course, is that the projection of one of these lines is going to be dense. So we are going to obtain a partition of the torus in immersed submanifolds of dimension 1, but they're not embedded submanifolds because in particular they are dense. And what happens is that in the neighborhood of a point, okay, the distribution is actually given by a coordinate vector field. So the trajectories in one of these open sets in which the distribution behaves as a distribution given by coordinate vector fields are going to be like this. And these green lines are plaques. And what we can see, in particular, we have here two plaques that are this one and this one. They are also plaques. And so what we can see is that one of these sets in which the distribution behaves as a distribution given by coordinate vector fields, those sets are called flow boxes, essentially. What you have is that the intersection of one of the leaves with a flow box is going to be a union of plaques. But we can have many plaques. Indeed, we can have infinitely many plaques. Okay? So let us prove the Frobenius theorem. The Frobenius theorem says that the three following conditions are equivalent. The first one is that distribution is integrable. The second one is that distribution is involutive. And the third one is that in the neighborhood of every point, the distribution is up to a change of coordinates generated by the k-first coordinate vector fields. So let us show that one implies two. Okay? So let us fix a point in M, and we can consider an open neighborhood of this point such that the restriction of the distribution to U is trivial, is a trivial vector bundle. So there exists an open neighborhood U of C in our manifold M such that the restriction is trivial. In other words, it's generated by at every point by k vector fields. Okay, and now what we want to show, okay, it suffices to show that the Lie bracket of xi and xj belongs, that this is a section of f, so that at a point w belongs to fw for every I and j between 1 and k, and for every w in U. Okay, if we can prove this, the distribution is involutive. Okay, so let's see how we can do this. We can fix a point w in U, right? And because we have to prove that the Lie bracket of w belongs to fw. Okay, and what we know now is that distribution is integrable. So there exists a submanifold M of dimension k, an immersed submanifold, such that W belongs to N, and the tangent space of N at a point Y is going to be the fiber of our vector subbundle. And this happens for every Y in U intersection N. Okay? Very good. But in particular, what happens is that xi applied to y belongs to fi that coincides with the tangent space of n and y at y, sorry, for all y in U intersection N. This happens for every I. So these xi's are indeed tangent to the submanifold N. So there exists a vector field which is going to be defined in U intersection N such that I tilde and xi are capital A related. And capital A is just the inclusion of N in our manifold M. All right? This is just because we can restrict our vector field to N because our vector field is tangent to N. Okay? But now what happens is that because of the covariance of the Lie bracket of xi tilde and xj tilde, and the Lie bracket of xi and xj are related by the inclusion. Yeah, and the first vector field is a tangent vector field on N. So the fact that these two vector fields are capital I related implies this is a vector field on N, and then what we get is that this Lie bracket at every point Y is going to belong to the tangent space of N at Y for every Y in U intersection N. Okay, but this is just the fiber of our distribution, and in particular W belongs to U intersection N. So we get in particular that the Lie bracket of xi and xj at w belongs to fw. And this happens for all I and j between 1 and k and w that belongs to u. So we get that the distribution is involutive. Okay? Let us see now that 3 implies 1. 1 is that the distribution is integrable. 3 is that locally and up to a change of coordinates is the distribution generated by the k-first coordinate vector fields. But if we have that every point has a neighborhood U, an open neighborhood, such that the restriction of F to U is generated by the first k-coordinate vector fields, okay, what happens is that then the integral manifolds are of the form are the indeed the level sets of the map xk plus 1, xk plus 2, and so on till xn. All these are integral manifolds. So by through every point we have an integral manifold. And so the distribution is integrable. Okay. Next, we can consider 2 implies 3. Okay. 2 is that the distribution is involutive. And 3 is that locally we can consider that it's generated by the k-first coordinate vector fields. Okay. Since the Frobenius theorem is a local theorem, we can suppose that we are working in a neighborhood of a point, and then we can suppose that we are working in Rn, and the point is the origin. So we're working in a neighborhood of the origin. And what happens is that then we can assume, by considering a small neighborhood of the origin, that our distribution is indeed generated by k-vector fields, right? What happens with these vector fields is that they are going to have this expression where these are C-infinity functions defined in a neighborhood of the origin, right? And then we can consider the matrix, okay, in which the lines are the coefficients. The line I is given by the coefficients of xi, okay. And what happens is that since these vector fields are independent at 0, then as a consequence, the rank of this matrix is exactly equal to k. Okay, has rank equal to k. So there is a minor in this matrix, a k times k minor, whose determinant is non-vanishing. So let us assume that it is the first one without lack of generality. We have that the first minor in which we are considering all the lines at the first and the first k columns has non-vanishing determinant. What we can do by some very elementary linear algebra, okay, is noticing that the distribution can be generated by other vector fields. But now the vector field ij is going to be the partial with respect to xj and some, let's call it p of jl partial with respect to xl, but L varies between k plus 1 and n. So if we consider just the first k components of yj, all of them are 0 except the component of index j, which is equal to 1. And this is possible, this is really linear algebra. Okay, so we have all these vector fields. Okay. What happens now is that by hypothesis, the distribution is involutive. And so if we consider the Lie bracket of yi and yj, it has to be a linear combination of the yls. But it is very, very, very easy to see by applying the definition of the Lie bracket that the first k components of the Lie bracket are equal to 0. So it's going to be something of the form C super ij sub L, something like this, partial with respect to xl from L equal to k plus 1 to n. Okay, this is very, very easy. That happens for every pair I and j. But of course, if this Lie bracket is a linear combination of vector fields y, and the first k components are 0, this can only happen if this Lie bracket is identically 0. Okay? Otherwise, it's impossible for this Lie bracket to be a linear combination of ILs. Okay, here we are using that the distribution is involutive. And now we have in a neighborhood of our point k vector fields that generate the distribution and that they commute. And at that point, we can use the rectification theorem that we saw in a previous lecture. So in this case, because it's going to be like this, after a change of coordinates by the rectification theorem. We have to use, of course, the rectification theorem for k vector fields that commute. And so we get the proof of 2 implies 3, and this completes the proof of the Frobenius theorem. The goal of the last few lectures was introducing and proving the Frobenius theorem. But obviously, we needed to introduce the Lie bracket because, in particular, the characterization of integrable distributions provided by the Frobenius theorem is expressed in terms of the Lie bracket, okay, the involutive condition. So first, we introduced the Lie bracket and studied its properties. And for such purpose, it was very useful to identify vector fields with derivations. Thank you for your attention.